I must confess, well, two things. One being almost last. Some of my points probably were made before. Maybe I'll make them in a different way. Redundancy is good for education. Just say that rather than I'm bored. I've heard this before, please. The other thing is that, I have a really poor memory these days. And when I started doing this, I looked at the session title for this session. It had to do with, it didn't mention forensic. It had to do with statistics. And I said, Jeff, this is about forensic statistics. And so I started writing something. And then I went back and looked at the title for the whole, 3 months. I said, oh, it is forensic. So I'm going to talk a little bit about some statistics that are not usually forensic, but the principles, in a sense, apply. To begin with, let's see this. I originally began. That's the mic. Oh, this is the mic? I don't know. Whatever it is. You can see what I say about memory. I don't know how these things work. I probably don't need it. That. Maybe the stick is better. What? No. That's this will be better if I know how to use it. Okay. No, I don't want to do that. Okay. So I thought of this as Variety of Statistical Challenges. That was my original title. But then I thought, no, that's not what the issue is. That there are actually very few what I would call statistical challenges in forensic science. Not that there are none. We heard some about mixtures and so forth. But when I was very new, there was a huge statistical challenge about how to deal with categorical variables in a multiple variable format. And then later there became a huge challenge about how to deal with selection bias. And the history of the development of statistics is dealing with these kinds of new challenges in terms of modeling and other issues. But for most forensic science, that's not the issue anymore. Indeed, often simple is better. Courts can be suspicious of things you do that are actually statistically good. You use multiple imputation to deal with missing variables, and the court may say, wait a second, you're just making up stuff and putting it in here? So in a certain sense, for lots of reasons, communication, other reasons, the challenges are not to the mathematics of the statistics. The challenges are actually to the statistics themselves. And those are the challenges I want to address. Now I got to figure, okay. First thing I want to talk about are legal and statistical models. Before I do this, let me just point that one of the reasons why we have all these challenges, I'm missing a slide. That's okay. Here it is. Let me tell a little joke, if I will. I'm not that conversant with football in the British and continental sense, but I know a little bit about it. But there's a joke that I'll analyze from baseball. A manager of a football team, one of the greatest managers of all time, dreamt he died and he went to heaven. And as soon as he got there, God asked him, would you please organize a football team for me? And he looked around, and there was Pele, and there was Ronaldo, and there was Beckham, and there was Maradona, and there was Messi. And he just, oh my God, this is incredible. So he organized 2 teams, and the only team that might beat his first team was his second team. And it was, but they play hundreds of games, and then just when he thought everybody was in peak form, he gets a call. And it's from the devil in Hades. And he said, I've just organized a football team. I'd like to play your team. And the manager said, well, we'd be delighted to do that, but I got to warn you, you don't really understand. I have all the players. And the devil says, no, you don't understand. I have all the referees. That is the relationship between statistics and the law. The statistics may have the players, they may have the quality, but the law has the referees. And the law sets the parameters of relevance and poses the question the statistician must answer, or the statistical scientist. And these may not be the questions that the statistical expert, the forensic expert, is best positioned to answer, and the standards of proof may not be statistical standards, but we must live with them. So let me give you a series of issues that are challenges. One are the legal and statistical models. The best case is probably jury discrimination. We have some experts here. Joseph, I know, is an expert. But this is really terrific in one sense, because the statistical and the legal models almost overlap completely. The ideal legal model of a jury is a random selection of jurors from a population. And if there's one thing you learn in Stat 101, it's the binomial and how to do that kind of statistical exercise. So you have this apparent mapping, and this is probably as good as it gets for the articulation of legal and statistical models. But how good is it? What are the characteristics of the relevant population? It's not just everybody living in an area. And how large of a deviation is required to trigger a legal finding? The lead case in this illustrates the problems. It's a case called Castaneda v. Partida, a 1977 case, and the court said, oops, again, I keep hitting the wrong thing. As a general rule, for such large samples, if the difference between the expected value and the observed number is greater than 2 or 3 standard deviations, then the hypothesis that the jury drawing was random would be suspect to a social scientist. There's all sorts of problems with nothing with the statement in a sense, but all sorts of problems in the context of the case. This was not a petty jury case. This was a grand jury in the first place. But secondly, and more important, this was not a system in which one would expect random selection to occur. This was a state that used what was called the key man system, in which the court appoints a number of community leaders and says, you select the grand jurors from among our upstanding citizens. What could be less random than that? And the Supreme Court had in fact approved of that system and said that's fine. So how in the world can you apply this statistical model, particularly in this county where Mexican Americans dominated the county politically, and they were the ones claiming they were discriminated against. But 79% of the county were Mexican, as were 50% of the grand jury. Now, the difference between the expected and the actual value were huge. But what the Supreme Court is actually doing here is they are changing the legal rule that they announced when they said that that grand jury key man systems were okay. They were in essence saying, yeah, they're okay, but if they are too deviant from the population of a county, they're not okay. The real rule is, yeah, you can do it this way, but actually it has to look as if it were a random selection with respect to race and ethnicity. The state argued that married women with changed names, Anglos, might have married Hispanics, and therefore the 79% was wrong, or some of these people might be non-citizens. And these are legitimate arguments about the base. This was the Supreme Court changing. The other thing which gets me, always got me, was this, before I leave this, always got me was this 2 or 3 standard deviations. I mean, there's a huge difference between 2 standard deviations and 3 standard deviations. But on reflection, I don't know if I'm giving the court too much credit. This could represent a kind of Bayesian thinking of them, that in some cases with lots of other evidence, maybe 2 standard deviations would be enough. But if there's very little other evidence, maybe they would want to just be much more confident about the reliability of the statistic they had. Okay, but that is good. But then you get very common models, regression models that are used in employment discrimination, antitrust, etc. And this is not so good a case. Consider the right legal model is very important. Consider Sobel versus Yeshiva University. First of all, in this case, the case arose it was a sex discrimination case. It rose very early after the passage of the act prohibiting sex discrimination. It was clear that women were getting paid less at yeshiva when you control for factors like rank and other things than men. But the issue was that a lot of this discrimination apparently went back to what they were earning before the act was passed. And if you controlled on the incomes they were earning already a result of discrimination at the time the act was passed, then a lot of these effects would disappear. And that's what happened. The case was dismissed, or it was about to be dismissed, but the Supreme Court had an intervening case in Braesmore in which they said, no, it doesn't matter whether the sex disparity in salary is pre or post-act. So you had to go back and redo the thing with the correct legal model because the legal standard had changed. They're also, with regression equation, the right scientific model, which can be very difficult to determine. OLS is typically the default, and perhaps for good reasons. The coefficients are easy to understand. The courts sort of understand it, they get educated in that. But it might not be the best functional form given statistical considerations. More important is the issue of the included variables and whose specifications of the model should be taken as gospel, if you will. And here we have a case called VCU, Virginia Commonwealth University versus Smith, a very interesting case. Virginia Commonwealth University decided that it wanted to rectify salary discrimination on its own. So they did this regression analysis in which they decided that the average woman at VCU was earning like $1,800 less than the average man when you controlled on a number of variables. The independent variables in their model were the national salary average in the same discipline and rank, whether they had a doctorate, their tenure status, whether they got quick tenure, which meant that they didn't take too long getting their first promotion, their experience, whether they served as a department chair, and gender. And when they got this number of like $1,800 or so per person, they then multiplied that by all their women faculty. They then set up a separate salary pool that had 400,000+ in it, which was the multiple of the individual disparities. And having done that, they then individually looked at each woman faculty and gave her a raise that could be from 0 to, I think, maybe as much as $40,000 in one case or some.
Is $1,800 a year?
$1,800 was the average salary disparity between men and women controlling. Per year. So these are annual salaries. So they did that, and then 5 men had the nerve to come in and say, we object to that. That's discrimination against us males because there's a separate salary pool that only women are eligible for. And the court decided for the male objectors on the ground that there was no measure of productivity included in the regression equations that the university had offered. There are numbers of problems with this. One problem is they had a number of proxies for productivity. I mean, one of their proxies was quick tenure, which requires, being particularly productive. Another proxy was serving as department chair. Now, they never seem to have explained that these could be proxies for productivity, so it may be partly their fault. But even if they had, the judge was set on this. But what this also does, and the problem it really illustrates, is what I call sort of the whose variable problem. If a variable is missing from a regression analysis, which is arguably a legitimate control variable, whose responsibility is it to put it into the analysis? Is it the person who offers the initial regression, or is it the objector? In this case, all you had was an objector who did not even do an analysis of his own. He just read it and said that it should have this variable in it. And I think that's a difficult problem, and I think it depends on how core and how obvious and how available the variable is. The university in this case argued that they really had no way of measuring productivity that could apply across the board, because in history they write books, in chemistry they write articles, in this place they write monographs, and different rates are, et cetera, et cetera. And I think this case was decided wrong, and if the objection was made, the plaintiff should have had the burden, but that's neither here nor there. But the other problem is model mischief making. We want to ensure fair, transparent, relevant, honest statistics, but this is difficult when you have a system, as in the US, where these studies can be done in private, where you can have 4 different people do a study and only present the one that you like the results of, when the people who are doing the study know the results you want to get. And They can choose variables. If they're the plaintiff, the variables to maximize what's going on. If they're and attribute it to, say, sex or to market concentration or whatever they want to. If they're defendant, they might add lots of proxies to sort of minimize the effect that seems uniquely associated with the key variable. There's p-hacking. They can try 30 different approaches until one yields significant results and use that functional form or that set of variables. They can avoid robustness checks. They do it once. They love the results. That's it. We're not going to look at anything else. They can ignore effect size. They can use unjustified assumptions. So that's why I say that regression models are, in a sense, the bad case, but they're used all the time in the law. Okay, second point. Second challenge, answering the law's question. But the question to be answered is not the statistician's question, it's the law's question. The science question may be, how likely is it that the DNA of a random person will, like the defendant's DNA, match the crime scene sample? And in the usual case, we have large amounts of DNA, and you can use standard techniques. It's an easy question to answer. And you can fudge things by, multiplying it by 2 or 3 times in case somehow the reference sample's not random, and you get an answer that's not going to mislead in that sense. But the law's question is not that. This was a point made very nicely by maybe the first paper or one of the first 2 papers we heard in this conference, that the law's question is how likely is testimony reporting a DNA match if the crime sample were left by somebody other than the defendant. This requires not just accounting for the random match probability given the suspect population, but the likelihood of laboratory, and I should have added, police error, sample contamination, mislabeling, subjective judgments, perjury. Whatever these figures are, they are much, much higher than the 1 in a trillion or 1 in 100 billion random match probabilities. But these are the ones that correctly guide the lawyer. So you have to answer the law's question to not mislead and overstate the implications of your evidence. But there's a complication, because a 1 in 1,000 probability of receiving testimony of a DNA match, if it was not the defendant who left the sample, is not the same as a 1 in 1,000 probability that a random person would have matching DNA. This is error on a base rate of 1 in, let's say, a trillion. This one here. This is actually the probability. And this figure, if it were, say, 1 in 1,000, or anything but an astronomical number, and this would apply for other kinds of testimony than the large sample DNA, this implies there are other matching people. In this thing, I have Bill here, so I got to be careful what I say, but there is something to the defense attorney's fallacy. Unlike the prosecutor's fallacy, the defense attorney's fallacy is not fallacious in the abstract as a matter of logic. It's fallacious because it ignores all the other evidence in the case and what the base rates are. So if all you had was testimony 1 in 1,000, and you have a population suspect of a million people, there are lots of people out there who might have left the sample. So answering the law's question. And this is a similar issue with other identification evidence like fingerprints, handwriting, bite marks, etc., except the objective other match probabilities are higher, the uncertainty is greater, and the subjectivity of the analyst is greater. Ironically, this may make the problems less important because the jury is not likely to be overwhelmed by the core number, and you will naturally focus in on these kinds of issues like subjectivity, uncertainty, etc. So this is really interesting given the talk I just followed, but the third challenge I had without any consultation was acquiring the necessary statistics. This is a problem with forensic evidence in general. We need to estimate error rates, even for the most reliable, and we don't do a very good job on it, for example. We have proxies for errors, lab accreditation, individual certification, training experience, and these are treated in court as if these will tell us what we want to know. They are proxies of very uncertain value. And I say uncertain partly in the sense we don't know how good these proxies are. We just kind of, as professionals, assume if the lab is accredited, they don't make many errors. The best way, of course, is through proficiency testing. But open testing, at the very best, sets lower bounds. Tells us how much error is completely unavoidable. When people actually know they're being tested, and they're taking extra care, and their promotion may depend on it, this is the number of errors they make. What we really need, of course, is blind, double-blind proficiency testing, but the labs point out quite accurately, as do the agencies, this is very hard to do. It's expensive. Of course, it takes time away from, and you really need numbers too. You know, if you just do is sometimes they've had efforts at blind proficiency testing, but what are they? 1 or 2 samples. You need large numbers to be able to set error rates. And suppose you have a history of error, and a lab has made, you know, reasonably substantial errors in whatever analysis they do. Well, the lab may say, and they may be honest when they say it, look, you're right. As soon as we saw these results, we changed our protocol. We used to have a situation in which there was a real danger of contamination of DNA in our lab, but now we do it this way. We use 2 separate rooms, and there's no danger. Well, they've said it so often, however, that one wonders, you know, what is introduced. But basically, this is right, and good labs, of course, will correct. And whatever the earlier rate was, it won't be the later rate. And then we have, sadly, some perjury, which is almost impossible to estimate. And we have these data needs. Many and this is what we just heard about. Many forensic technologies need to validate or set bounds and assumptions. Are fingerprints unique? We don't know. But even if they were unique, we have no idea how unique a somewhat fuzzy print would be. We have no idea how much, when you have like a quarter of a print is all that's left, how unique that is. And there's almost infinite variety of degrees of indisputability. You know, if we have 10 fingerprints and we have 10, you know, that were taken by the suspect and they left 10 fingers on glass at the scene of the crime, yeah, they may be, for all intents and purposes, unique, even if we don't know it. But in the range of actual casework, we just have no idea. How unique are bite marks? What do we know about blood splatter? We don't have this information that we need, and that's the challenge. Arson's a cautionary tale, as are, I could give many cautionary tales, but where there are ideas about how hot a fire could be if it was natural versus arson, and it turned out that's dead wrong. But there are people who've gone to had the death penalty because of testimony about that. And one can go through the history of forensic science and see it's littered with failed technologies and people who were imprisoned or perhaps even executed because of it. You can, you know, paraffin tests, neutron activation analysis, voice stress analysis, and the court has been very prone to accept things that are kind of identified ad hoc or become fads within a small section of a community. And yet we don't know. And we need to assess utility. How much better, if we're talking not about, you know, looking at inks and things of that sort, we're just talking about handwriting recognition experts. The law, at least in the United States, says that you can introduce an expert if something is sort of beyond the ken of a lay jury. Well, if lay jurors, and let me say there is something to handwriting experts. They do better, according to the research I've looked at, though not all the research, but they do better than lay people. But maybe not that much better. They get 70% right, the lay person gets 50% right in a similar test. Is that enough to justify bringing an expert in? And if you do bring an expert in, what does it mean? How useful is it to the jury to know that? We don't know that.
Are you okay with 5 minutes?
Yeah, I will certainly finish in 5 minutes because I'm getting to the end. The last challenge that I want to talk about is our communication challenges. There, of course, is a sweet spot that we should aim for. The sweet spot is obvious. We want fair and appropriate persuasiveness. But the incentives in a trial, at least in an adversary system like the US system, run entirely contrary to hitting that sweet spot. The offerer wants to exaggerate the probative value, and the opponent wants to denigrate the probative value. How does one deal with that? And then we have to make statistics understandable, another key issue. It's difficult to do when both objective match rates and false reporting rates should be made. And there's a study which, it's only one study. I don't believe you should really accept anything on the basis of one study. But nonetheless, it's pretty sobering. It's a recent study by Jay Kohler in which he had subjects look at shoe print evidence, and there were basically two conditions. One condition was you sort of got the random match probability of a shoe print is 1 in 1,000. The other condition gave you the probability of getting the witness's testimony, which was also set at 1 in 1,000. So one probability is open to all sorts of other sources of error. The other probability includes all sources of error in the probability. It made no difference with the subjects. Not only did it make no difference, but cross-examination did not help at all in this study, and it did not help even when it focused in the first case on the sources of error that were not included in that probability. And the jurors, the mock jurors, they failed to differentiate between the expert who had not simply said the shoe left the print, and that was all they said, and the expert who gave a probability of 1 in 1,000 and told about and included in that probability all potential error. So if you want to make statistics understandable, and this is the way subjects are reacting, we must do more. People like Bill and others, Jay, are trying to do experimental research exactly on this topic, and often what they learn is not very discouraging, but hopefully if this research were adequately funded, a counterfactual that I fear will not occur, one could build up a body of knowledge that would do this. And finally, I say Bayesian dreams. We've heard about this. A lot of these problems we could make a lot of headway on this, at least certainly conceptually, but maybe even really if we could get Bayesian perspectives. So something like my example of the handwriting expert, you put that in a Bayesian framework, it's easy to see what the real probative value and what is added in, unlike the testimony of there's a 70% chance that this is the handwriting of the person who did it. And you go through this, like reading particularly all this forensic evidence, oh my God, if we could only apply Bayes, we'd be able to give them something that's reliable. But we can't. That's it.
We have time for one question, if anybody has one.
What do you mean by but we can't?
Excuse me?
You said but we can't apply Bayes. Do you mean
Yes.
I mean that given the jurors, at least in the jury system, we heard how it is being applied in Holland, for example, but the jurors are unfamiliar with it, the judges are unfamiliar with it, we often don't have the information that we need in terms of solid priors.
so there's a few different...
But I still think the Bayesian perspective can inform the expert witness's evidence even if not presented explicitly in a Bayesian form.
It should inform the expert. Then we go back to my incentives to present things as persuasively as possible for your side. Maybe it'll inform one side's expert.
We can spend the rest of the semester talking about that.
Yeah.
Okay, so our next question is